Hello and welcome to Group 1's presentation of torque, power, work, and energy in cycling. We're going to start out with torque, which is a force applied off of the center of rotation to an object. And this is pretty important for biking because we're applying torque to the pedals, which has an output torque to the wheels that pushes on the ground to make this whole thing work. And a torque is a vector quantity measured in Newton meters and can be static or dynamic, which has an interesting component with biking because it means that we're actually applying a static torque when we are coasting at a constant speed on the bike. So Newton's first law does apply to rotational systems as well. So an object rotating with a angular velocity will continue to rotate at that same angular velocity until acted on by an external torque. And it's good to bear in mind that torque also applies to leaning on the bike, and in that case the torque is coming from gravity. Gears give us a unique advantage on a bike. We would not be able to pedal fast enough to maintain the types of speeds that we want when biking without gears to allow us to adjust and modulate the speed that we need to pedal to produce the rotation at the tire. And when it comes to angular momentum, if we're traveling in a straight line, both the front and back wheel will have the same angular momentum, and angular momentum goes out horizontally to the rider's left if we are moving forward from the center of each wheel. Moving into work, power, and energy. Work is force times distance. Remember, that's distance and not displacement. So if we go a full pedal stroke around 360 degrees, we did that full distance of the circumference, so it is a positive amount of work being done. Power, on the other hand, is force times velocity, or you could look at it as work over time. Being that cycling is continuous, the time part is going to be a large value, so it's usually better to measure it as an instantaneous value, and we'll get to that in a minute. Energy can come in a lot of forms. The big ones we'll see here are potential energy and kinetic energy, and heat energy doesn't play an important role, which we'll get to later. Work is best measured at the pedals because that's the work that we are doing on the pedal, and we know the exact amount that the pedal goes around as well, which is useful for that. If we wanted to test the efficiency of the bike, we could be comparing the work done at the pedal to the work done at the tire on the ground as well. And power, again, is measured best as instantaneously, and we would do that by taking instantaneous force and multiplying that by the instantaneous velocity. Gearing, again, does make power a little bit obsolete because of our ability to control the rotational speed that we need at the pedal, but it is still going to show up because we're still doing work, or we're still applying force at a certain velocity. So even though we can control it, it's still an important component. Energy is best measured as the entire system, so that includes your body's metabolic energy stores, that includes if you're up on a hill, that includes any of that stuff that could be translated into kinetic energy. And the kinetic energy, as we are going to look at it, is the speed of the bike, essentially. Or if we're talking about a stationary bike, that can also be the rotation of the wheels. And of course, heat energy. Now, the factors to kind of control how we're applying energy and control the forces that we see at our joints is going to be how we adjust the bike and how we set the bike for comfort and performance. Handlebars are adjustable, and you can also adjust how you place your hands on the bars for different scenarios or situations. The seat height is, of course, adjustable as well. Many experts say that you should be between 25 to 30 degrees flexed at the knee when the pedal is at the bottom of its rotation. The seat can also be slid forward or back, and another tip is to pay attention to where your knee is in relation to the crank, because if the knees get too far in front of the crank, that increases the force placed on the knee during extension as well. Foot position is, of course, modifiable, and that can slide forward or back. Typically, it's recommended to stay on the ball of the foot so it doesn't put too much pressure on the ankles, and you don't want to go too far towards the toe because that can put more pressure on the knee. And, of course, the biggest risk of injury in biking for chronic injuries is to the knees and the low back. Looking at energy and collision. As we start moving, as we go from 0, where we have no kinetic energy, and all potential energy, depending on if we're on a hill, or also including our metabolic energy stores. Once we start moving, that starts to translate into kinetic energy. The bike is not a perfect mechanical system, so it's not perfectly efficient, so we only get about 90% of the energy that we put into the bike to come out, but still relatively efficient. And collision is not something you'd think about in biking, but actually when the tires hit the ground, that is a collision. When the tires rotate and collide with the ground, they deform. And when they come out the other side, they rebound back to their original shape, which is called restitution. The coefficient of restitution tells us how aggressively and how forcefully the tire will rebound to its normal shape. This coefficient goes up closer to 1, which 1 being the maximum, that's perfect rebound and instantaneous rebound, perfect elasticity. It gets closer to 1 as we inflate the tire more. And we see that on this chart, that as we inflate the tire more, we see a decrease in rolling resistance, showing the importance of the coefficient of restitution when it comes to the tire colliding to the road. However, if we go too far, the tire will actually become almost bouncy and not grip the road the way that we want. A stationary bike uses friction to provide the resistance for the rider to get an exercise. This is typically an adjustable band around maybe a metal wheel, and it takes the kinetic energy of the wheels spinning and converts it into heat through friction so that we can keep putting in more work without having to move the bike anywhere. And the brakes essentially are doing the same thing, but of course in this case it's to stop a moving bike, but it still is turning our kinetic energy into heat energy through friction. And we can see this if you touch the metal calipers of a disc brake, or the metal disc of a disc brake after a ride. It can be extremely hot because of this heat energy that's been created by bleeding off our kinetic energy. And that's all we have for you today. I hope you enjoyed our presentation on work, power, energy, and collision in cycling. Thanks.